Professor Yiyue Luo to give us an exciting talk.
Thank you for having me. My name is Yiyue, and I'm an assistant professor at University of Washington. Before I start, I would like to confess that I am not a roboticist, even though I really wanted to be. I'm leading the Wearable Intelligence Lab, where we are building smart wearables for human-computer interactions. But today I'm very excited to share some of our work on building scalable tactile sensing interfaces, both for humans, robots, and the tools that can be used by both humans and the robots. So as I'm coming from the human-computer interaction community, I would like to start the motivation from a human perspective. So humans engage in a diverse of daily activities through a sensation of touch. And such sensation of touch is not only on our hands, but also throughout our human body, on our torso, on our feet, and so on. And such sensation embeds tons of information. Let me try to hide the as an example, at this moment, as you are sitting on a chair, the tactile sensory systems throughout your body constantly capturing the tactile information, feed the information to your brain, which process the data and generate signal to drive the corresponding muscles. And therefore, you will be able to adjust your body posture and balance while you're sitting on the chair. And on the touch side, we are very excited on building intelligent interface that will be able to enhance such sensation of touch by recording, modeling, and augmenting through tactile sensors, AI agents, and haptics. But we are facing this challenge of touch sensation throughout our human body. They also serve us 24 hour a day. So the research questions comes in how to efficiently scale up the tactile sensing interface in terms of coverage area and how to seamlessly integrate such tactile sensing interface in a flexible, breathable, and very thin form factor. And the same challenges also appear on robots, not only on humans, as we are going from Dester's hand to robot dog to even larger scale system like humanoid robot. Ideally, we should have full coverage area on the robotic system in the same flexible form factor on the surfaces. And with that, we are proposing a digitally designed and fabricated sensing and haptic interfaces, both for humans, robots, as well as the tools that can be used by both humans and robots. And to start with, let's talk about capturing and modeling touch sensation on humans. So this was my work back in 2021, where we are presenting a full-size tactile sensing garments in a form factor of vest, socks, and glove. So each individual pixel here capture the continuous pressure distributions. The sensing functionality comes from the customized piezo-resistive fiber, where we'll be able to coat conductive stainless steel thread with piezo-resistive nanocomposites. And when we overlay two fibers orthogonally with each other, they form a sensor at the intersection where a piezo-resistive layer is sandwiched by two conductive electrodes. When you press it, the resistance will drop, and therefore it will be able to convert pressure information into electrical signal. And by leveraging such fibers, we'll be able to apply it on digital machine learning, which is industrial scale textile manufacturing techniques, enabling users to computationally design and automatically fabricate textiles with complex shaping, textures, and color works in a stretchable and breathable form factor. And here's an example how we are automatically integrating functional fibers in textiles using the machine. It will be able to form fabrics that is soft and flexible and stretchable, just like our regular garments, and allow us to fabricate a scalable tactile sensing matrix with thousands of sensors on there. And with that, we'll be able to capture diverse physical human environment interactions in a continuous and real-time manner. This includes doing different kind of exercises where the tactile sensing socks, different kind of human object interactions with the glove, and so on. And we are also able to apply machine learning techniques to extract features and insights from such high dimensional data. And here's an example. We are using convolutional neural network to regress the full body pose by only looking at the tactile sensation from a pair of socks. As another example, we'll be able to project the tactile sequences captured from a human's back during different kind of sitting postures on the furniture into a 2D space through Disney and achieve a classification accuracy up to 94%. And beyond capturing physical human interactions using wearables, we also present the same kind of functions by using an environmentally integrated tactile sensing interface. So we do it in a carpet form factor. So this carpet spans 36 square feet with more than 9,000 sensors. And the good thing about it is it will be able to capture the interactions with whoever user is walking on it. And it also works for multiple users, not only to the single user who's wearing the garments like the previous examples. So similar with the previous one, we'll be able to capture the real-time pressure distributions between the human and the ground. So you can imagine it as like a camera, which is looking up from the bottom, featuring on the human-ground interactions. It captures the continuous pressure distributions in the pixelized format. And we can treat all those tactile frames just like images and video information and apply convolutional neural network to regress the full body pose by only looking at the tactile sensations from the carpet. And it also works both for single person and multi-people scenarios with a diverse set of daily activities. And such system has been applied for AR, VR applications, as well as assistive walkers for assistive technology. And I would like to briefly mention that beyond sensing, we also work a little bit on haptics. So here is a digitally embroidered smart glove with tactile sensors at the fingertips with the vibrotactile haptics on the inside of the glove. The whole glove is manufactured by digital embroidery, which is also a automatic manufacturing process, allow us to customize the glove with arbitrary sizes and different layouts in a relatively accessible manner. And by leveraging such system with both input and output modality, we are able to transfer the tactile sensation. So here's an example of how we transfer the sensation between users. So in the piano learning scenario, we'll be able to transfer the sensation of touch from the teacher to the student, and therefore promote the learning performance and learning efficiency. And similar setup, it's applied on the teleoperation setup, where we equip the parallel gripper with tactile sensors and transfer the sensation to the human, which has their vibrotactile haptics on their hands, and therefore they will be able to manipulate soft and deformable objects in a more robust manner. And with this, I would like to switch to equipping robots with this kind of human-like tactile sensing capabilities. So this is the same work as the first work I presented, where we can use a digital machine knitted sleeve to conformally cover this KUKA arm with this large curvature at the joint. So in a conformal manner, we'll be able to equip 700 sensors on it, which is evenly distributed over the arm and to capture this human-robot interaction. And similar setup can be applied on specialized gripper for different kind of contact-rich manipulation, such as egg picking, water bottle manipulations, and scissors manipulation. And here's a more recent example where we are able to use a bimanual gripper with tactile sensors integrated on it for delicate manipulation. As a lot of speaker mentioned earlier, when you are doing in-hand manipulation, the gripper itself is occluding the vision information, and therefore the tactile information inside of the hand is very critical for this kind of task. This is also a very recent work where we are trying to leverage the scalability of our system to cover a bigger area. So here is tactile sensors on the back of the robot dog, which will be able to allow us to capture the real-time tactile sensation and therefore allow it to carry such cylindrical object during locomotion without dropping it. And all of these tactile sensors is enabled by a digital fabrication process, including embroidery and laser cutting, which is automatic fabrication, so it's very easy to scale up with minimal manual labor. And then we can also automatically adjust it to arbitrary shapes and designs as well. And this, by integrating the tactile frames into the learning and policy, we'll be able to have the robot dog carrying diverse set of objects in a robust manner. And so when we are talking about robots, we are always talking about potential for some superhuman capability. So all of the touch capability I talk about is actually very similar to humans. So we also work on some superhuman capability by using electrical impedance sensing. So here is a gripper that is equipped with an array of electrodes. And electrical impedance sensing is by using pairs of electrodes. One pair of electrode will be injecting current, and then other pair will be receiving current. And by comparing the difference between the input and output signal, we'll be able to infer the impedance profile across these electrodes. And by doing so, we can have we have a digitally embroidered electrode array, and by having a microcontroller that can achieve such active sensing mechanism, we can equip this parallel gripper with such active electrical impedance sensing. And by grasping an opaque container and pouring different liquids in there, we'll be able to capture the dramatically different impedance profile of different liquids in this opaque container, and therefore to classify what kind of liquids in there. And also during the manipulation, we are rotating the water profile in terms of the container, which is changing the impedance path in this container as well. And therefore, we'll be able to regress what is the liquid state inside of this container. And with that, I would also like to talk about the third part of the talk, which is about equipping sensorizing tools instead of sensorizing humans or the robots. So tool using is actually a hallmark of intelligence. It's one of the main things that makes human a human. So I think when we are trying to infuse this kind of intelligence to robot, researchers has been explored how to let robots to manipulate tool for very delicate tasks. So this is how a robot to manipulate a chopstick, which is, so I've been using chopsticks in my past 20-something years and I'm still not good at it. So this is a very delicate and complex task for robots. And with that, humans use diverse set of tools every day. So imagine when you're cooking in the kitchen, you would grab a knife to cutting, grab a tone to distribute the food, and then use a stir fry to make the food. And you do it in a long sequence manner in a very natural way. So when we are trying to infuse such intelligence to robot as well, we want to make sure that on the human side, we are also manipulating the tools in a very natural manner. And therefore, we are proposing to sensorize the tool instead of sensorizing humans' head, because what we observe is that when humans wearing the glove doing different kind of activities, the glove is actually changing their behavior dramatically. And therefore, the data we are recording is not the most natural way of us interacting with different objects. So here, example, we are mounting like this modularized sensors on different set of tools. It comes with a SLAM camera for the post estimation of the tool, as well as torque sensor at the handle of it. So as a user, you come in the kitchen and you grasp the tool, and then you can perform the task very naturally, just like what you do with the regular knife. So I really like this knife example, but I cannot bring it because of safety issue. But I bring the other chopsticks and the brush with me, which is behind the room. So at the knife, we not only have torque sensor, we also have the sensor at the end effector of the knife. And therefore, when we are manipulating with the knife, when we are trying to make this action, it will be able to capture the interaction between the knife and the foot as well, and capturing the data from that perspective. So this is a very natural way of capturing data of how human using different kind of tool. And we can also use the same setup on the robots as well. So here is a teleoperation setup where the users are naturally grasping the tool and then to perform the task. And then we have a twin on the robot side, which is mounting with the tool in a robust manner and mapping the action to do the task. So notice that this user is cutting something, and then he's going to the background and then changing from the knife to a brush. And at the same time, the robot is also going to change the tool from the knife to a brush in order to map the same action. And we also build this robust tool changing setup, which allow the robot to grasp the object very securely, and then perform the action with relatively straightforward control. And these are just some examples of the tools that we are sensorizing. The modular sensor is a relatively generalizable way that will be able to plug in on different tool with the handle or with the articulated mechanism like chopsticks or scissors and so on. And with that, I briefly talk about some of our work by having tactile sensors on both humans, robots, and the tool. And I would like to highlight that I do see touch is a very useful and skyrocketing sensing modality beyond vision, audio, and text. So a lot of people has been mentioned, a lot of this digital modality has been benefit from having extensive data. And to me, I feel like the extensive data benefits a lot from the off-the-shelf sensing and output interfaces. Like imagine you can buy a camera, buy a speaker in a relatively low cost, and you can implement it in your setup very quickly. But that is not true for tactile sensing right now. So I would love to help democratizing the tactile sensing system to different community. So these are some of the work in my in human-computer interaction community, where we are building a design toolkit where allow users to input arbitrary 3D geometry, not limited to a human, but also a different kind of robot system. And then users will be able to interactively edit their tactile sensor designs, potentially with some hints from the AI agents to help them with the design. And then it will generate low-level fabrication instruction for immediate fabrication, either through laser cutting or some other more specialized digital fabrication mechanisms. And we are also working on the firmware, where we'll be able to have an adaptive circuit and firmware for efficient and adaptive data acquisition in a wireless way. And we are also open sourcing a lot of our designs, circuit, and control for broader usage, and feel free to check it out. And with that, thanks for having me here, and I'm open to questions.
Any way to get the user listed right now, or is that just something that you make it out?
So the thread is something we customized, but a lot of our tactile sensing system, everything is commercial. For example, there's no way I can go back. For example, a lot of this setup here, they are all based on commercial materials. We're using commercial conductive fabric and commercial piezo-resistive film, and then with also polyimide layer to do the encapsulation. So everything here is commercial.
But the thing is the fabric that it's a film.
It's a film. It's a film here. Yeah. Yes.
But yeah, they did very good work, and Well, speaking of tools, it seems like when you're working with tools, you have this interface to have the user hold something which stabilizes the tool. And then what happens, like, have you thought about like with the humanoids, for example, they use like off the shelf or they use like some hands, and they might not necessarily have those extra interfaces to help hold the tool. So do you think that some of your work would also apply to like humanoid with dexterous hand that are using those to flexibly handle different tools without like tool specific interfaces?
Yeah, so I think these are a completely different approach to me. So if it's a humanoid hand, it might be able to grasp the tool just like how humans do. But how we have tried it, the reason why we developed this tool changing thing is we find the hand is very complicated in control. And then when it's grasping the tool, it's a little bit not robust. So in order to quickly bridge the gap between how humans use tool and how robotic systems use the tool now, we are actually trying to make this more robust tool station now. I think there are two very different approach, and we are not sure which one is better at this point, but I think both works exploring.
Thank you for the excellent talk. So talking about different approaches, in my group, we've worked a little bit on some sensors, but I often get overwhelmed with the number of different types of sensors people are developing in different modalities. Do you think that there's, in your view, one sensor that is going to sort of be best for most scenarios, or is it really going to have to be, task specific?
That's a really hard question. At this point, I feel like it needs to be task specific. I guess it's just because people are still exploring and they don't know what kind of data is the best and what kind of information is the most important for generalizable robotic system. So I think once they figure that out, it will be more clear that what kind of sensors is the best for general usage. At this point, I see different kind of sensors has different advantage. For example, for the piezo-resistive one, the biggest advantage is it's very thin and it can easily scale up to very large coverage area. So it is possible to cover a whole humanoid robot that cover the full arm with a relatively low spatial resolution, not as high as gel side and the visual tactile sensors. But it will be able to achieve the capability very similar to human, which is low resolution, but they do have some kind of sensing on their body. But the gel side, well, a lot of other sensors, some are good at very high spatial resolution, some are good at doing shear sensing. So I think different sensors now have different pros and cons. It needs to be task specific now. That's how I see it.
For the piezo-resistive, how expensive is it to decorate a whole robot?
So the sensor itself is very cheap. So the biggest cost for us now, it's on the circuit side. So the material is like probably on this knife, it's only like $5-ish on the materials, but the circuit for PCB manufacturing like $20, $30-ish. I think the biggest constraint now is the cables. So there are a lot of cables coming out of it, which we don't want it on robots. Like you can see it here, there's still cables coming out from here. So I think a lot of this practical constraint we need to solve right now.